Hello everyone, this is the lecture video of section 12.7, first part of Calculus 3, Math 2533. Okay, so let's see. In chapter 12, section 1 through 6, we skipped section 12.5, but up to 12.6, we were studying double integral. When you have a function of two variables defined on a planar region, on the xy plane or uv plane, we define double integral of a function on the domain D as basically limit of Riemann sum. Function value, when you split your domain into fine grids, some small sub-regions, area times function value there, and add them up throughout the region, and take the limit. That was double integral. We can extend that idea to function of three variables. Here, let's say your function f is defined on a three-dimensional box, rectangular box. X from A to B, Y from C to D, Z from R to S. Okay? We use so-called direct product. X is in this interval AB, Y is in this interval CD, Z is in the interval of RS. Okay? Then, just like double integral case, we partition the whole region into fine grids. We will partition the entire box into from lump of tofu, we put fine, tough pieces of miso soup, for example. So along the x-axis, from A to B, cut, uniform cut, L, many subintervals. Along Y, M, many subintervals. Along Z, N, many subintervals. So delta X, each size of subinterval along X is delta X, along Y, delta Y, along Z, delta Z. That is total length divided by number of cuts. Total length divided by number of cuts. Same thing. Then we consider x0, x1, x2 all the way to xl from A to B. y0, y1 all the way to ym equals d. From r equals z equals 0 all the way to zn, which is equal to s. Okay? So the typical ones, right? You just add one more. In double integral, you have xi, yj. Now you have zk along z. So basically, you cut it this way, and then this way, and that way. So you will make a small pieces of miso soup tofu, right? Tofu and miso soup. So those are ijk small sub-rectangular box, right? This is ith interval along x, jth interval along y, kth interval along z, somewhere inside. ith one, jth one, kth one, somewhere inside. Okay? Then the volume of each sub-rectangular box will be delta x times delta y times delta z. We call it delta v. Alright? And then you choose any sample point in each ijk sub-rectangular box, small rectangular box. You choose a point anywhere you like inside the ijk sub-rectangular box, and then you evaluate your function at that sample point. Multiply that function value by the volume of that sub-rectangular box. You add them all up through I, J, and K. Triple Riemann sum of f. Then triple integral of function f over this box B is defined as triple integral f of x, y, z dv is defined as limit of ln n all going to infinity into m. Oh, this is L, M, M, f of x, y, j, k star. Delta. Limit of triple Riemann sum is what we call triple integral. If the limit exists. If the limit exists. If the limit exists, we call function f is integral over box B. Okay? So it's the same idea as double integral. You just have one more variable, one more dimension. That's all. It's a natural extension. Okay? Now, if we call it integrable function, if the limit of triple Riemann sum exists, and just like double integral case, if your function is continuous on box B, then it is integrable. Triple integral exists. Even more, if your function is continuous except for some finite number of smooth surface, you could have some crack here and there. But as long as discontinuity is limited on that finite number of smooth surface, and your function is bounded, does not go to infinity or negative infinity, then your function is integrable. Okay? Then, just like your double integral case, when you have a rectangular domain double integral, you are able to write it as an iterated integral in any order, as long as your function was integrable. Actually, if it is especially continuous, right? Just like that was called Fubini theorem. Just like that, we have also Fubini theorem. When your domain of the three-variable function f is this rectangular box, like this, then Fubini theorem of three-dimensional case says that if f is continuous on this box B, then this triple integral, this triple integral can be calculated as R to S, C to B, A to B, f of x, y, z, dx, dy, dz. Now, in double integral, you have two orders, either x dx, x followed the y, or y followed the x. When you have three variables, there are three factorial number of ways to arrange x, y, z in an order. So you have 6 different iterated integral, order of iterated integrals. Like, skipping this one, a, b, c, b. So dy, dx, dz. All right. What about this? F of x. So I didn't write everything in the lecture note, but let's write it. This is dx, dz, dy. This time y is at the end. Then rs, y at the end. And then AB, RS. DZ, DX, DY. Z. A. Okay? There are 6 differences. All of them are equal. Okay? So, because of this, when you have a triple integral of a function on a rectangular box, you just choose one of those orders, which give us easiest integration. Okay? Now, for example 1, z to the third. dv, where your box, rectangular box is 0, 1, 0, 3, 0, 2. So x is between from 0 to 1, y from 0 to 3, z from 0 to 2. In that case, so for this one, we can do it in any order in this case. So x, y, z, dz, dy, dx. You can do this, all right? Now, when your function is separated by multiplication, function of x only, function of y only, function of z only, when you do this, the innermost z integral, x squared y acts like a constant. So you can take out of the integral, right? And then you have from 0 to 2, z to the third dz, and then dy dx, right? And of course, x squared can be taken out of y integral. So everything will be just, integral of x squared. So let's do that. In this particular case, this is a constant, isn't it? With respect to y. This is already a calculated constant. So it can be taken out of the y integral. And also x squared is constant with respect to y. Z2 and okay. Once you take out of this, now this is a constant, right? These two constants can be taken out of the x integral. Just like double integral case, you can split it into z integral only, y integral only, x integral only. You can do that. So this is 1 over 4 z to the fourth, 0 to 2. 1 over 2 y squared, 0 to 3. 1 over 3 x to the third, 0 to 1. 16 over 4, so 4. 9 over 2. 1/3. 3, 3 cancel. 2, 2 cancel. It is 6. Okay? All right. Now, in double integral case, once you had in double integral, once you define the double integral over a rectangular region, how do we extend that one into general domain? That was by doing this. Think about bigger rectangle R, and then we define capital XY as same as f of xy. If xy is in the original domain D and 0, if your xy is outside of D, like this, right? In this region. Okay? And then we define double integral of f of xy over D as double integral of capital f of xy over bigger rectangular region. Just like that. Triple integral over a general domain will be defined same. So if you have some three-dimensional shape, three-dimensional region E, then we'll consider and think about big enough rectangular box. which contains this thing is inside, right? This is E. So we consider big box B to include the original domain of function E inside. And then we define capital F of x, y as same as f of x, y, z, f of x, y, z, x, y, z is in original domain E, or 0. Okay? Then, triple integral of original function on the original domain E is defined as triple integral of extension of the function. Over a bigger box. But we know that the function that is outside E will be 0, so no contribution when your points outside E. So the value must be same. That's why we define that way. Okay? But then how do we actually calculate this in practice? Well, in double integral, what did we do? We thought about, in double integral, we thought about type 1 and type 2. You remember? When your domain is, let's say, it's type 1 like this. Y equals G2 of x, y equals G1 of x. So your domain is written as A runs from A, x runs from A to B, and y for given y, given x, y runs from this value to this value, given G1 of x and G2 of x, right? So this point is x G1 of x. This point is x G2 of y, x. Y runs from G1 of x to G2 of x. Then double integral on this d, f of x, y. Okay. You were able to write it as similar to iterations in rectangle, except for instead of CD, you have a bearing, end values of interval. dy and dx. So you calculate inner integral first, integral with respect to y for some x. So this will be some expression about x, and then integral with respect to x. And you could do the same thing for type 2. So we will have to do the same thing. One more dimension, a little bit more complicated, but the idea is the same. That is, as you can see in the picture, we'll have to think about type 1. So type 1 is three-dimensional type 1 in 3D. Means your domain is a generalized cylinder. Okay? So Okay. This is D. All right. And then you have some surface here. Top surface as z equals u2 of xy. And the bottom surface. It's not necessarily planar, right? The bottom surface is the graph of z equals u1 of xy. And xy is in here. So your point is starting from here, ending here, going like this, inside. Okay? If you want, you can think about that one. For given xy, penetrating here and leaving here, right? So starting value is, this one is given xy, u1 of xy. And this point is given xy, u2 of xy. So, if your domain E can be written as xy is in some planar domain in xy plane, then z runs from u1 of xy, low bottom floor function, all the way to ceiling function. If you can write your domain in this fashion, then you call it type 1 in 3D type 1. Okay? Then, just like, I just wrote, the details, but this is exactly the same idea as the double integral case. So, in that case, your triple integral over E. Okay. Going through this way, and then we do from A to B, C to D, and R to S, and then from R to S, from R to up to this part is 0, from here to S is 0, so you just take it off, and then it's going to be, in the end, double integral D of from u1 of xy to u2 of xy. F of xy is z, dz, and double integral. So, for given xy, all right? So that would be type 1 case. And then, if D, now you have to do this thing. If your D, and this D is from A to B, and G1 of X to G2 of X, like this, just like that, then that double integral can be written as from A to B, G1 of X, G2 of X. And then this is dy dx. So you're gonna have triple iterative integral according to the type. Okay? Now, if your domain is, if D is, for example, if D is type 2 in two-dimensional way, that means if D is y from C to D, type 2 in xy plane, and h1 of y, 2 of y. If that is the case, then this will be written as C to D, h1 of y, h2 of y, see, dx dy. So this will be a function of z integral. So the whole result will be a function of x and y. Basically, the function of x, y will integrate this fashion or this fashion, type 1 or type 2 in the xy plane. Okay? So idea is similar. All right? So for this case, the full notation for E would have been what? X from A to B. For given x, y runs from g1 of x to g2 of x. And then for given x, such x and y, z runs from u1 of xy, u2 of xy. So if your E is given from the beginning, like this, then you can write it this way, right away. Okay? Or if your E was written from the beginning, written as x, y, z, c, y from C to D, h1y, x, h2 of y, and u1 of xy, u2 of xy. If you're given this way, then this is it. You can write it from the beginning. All right? So, analysis of the domain as type 1 and type 2, leading to the right form of iterated integral of double integral. Likewise, right analysis of the given domain is a type 1 or what other types. Like if you analyze your domain like this as a type 1, you can set up iterated integral accordingly. Okay? So that's what you see in the page 11, page 3 in the section 12.7. Okay? 3 and 4. Okay? Now, page 4, type 2 of the region. Now, type 2 in 3D is the most important thing was on type 1 was it's a generalized cylinder, right? Along the direction of z, right? So your projection onto the xy plane is our domain z. Type 2 will be now your generalized cylinder along the axis is x-axis. As you can see in the picture of the thing. So this is, generalized cylinder along, okay? Y. This is D, domain, X, Y, Z plane. Your domain is D, is in the YZ plane. And then there is a surface. That surface is now X equals U2 of YZ. Now here, this surface, the front side, back side of surface is the graph of x equals u1 of yz. So, for given yz point, you enter here, all right? You enter through this point, x equals u1 of yz for given yz, and you are here and then exiting out at the point u2 of yz and then yz. Okay? So, in this is type 2. All right? Type 2, 3D. 3D type 2 is when your generalized cylinder has in the direction of x-axis. All right? The axis is parallel to the x-axis. So if you can write E as x, y, z, now yz is in the domain of d in the x, yz plane, and the forgiven yz, x runs from y1, u1 of yz, u2 of yz. Okay? If the region is analyzed like this, then triple integral over E, f of x, y, z over E, is just like the way we did this. Double integral over d of, and the x runs from u1 of yz, z of f of x, y, z along dx. And then this is, after that, this is going to be resulting ones will be function of yz. Right? With respect to x integral, consider y and z just like a fixed number. So the whole expression will be a function of y and z. And then you do double integral in yz domain. Okay? And finally, and then of course, those yz double integral will be done by type 1 and type 2 in 3D version, right? In double integral. Okay? Likewise, your type 3D version of type 3 will be what your domain is. No. Some surface here, all right? This is y equals u2 of xz. This side of surface is y equals u1 of y equals u1 of xz. And this is domain of d in the z y and x. All right. So in that case, it's so hard to write it again. So then this is xz. xz, y runs this one. xz. Then this is y runs y. xz. That would be this. Okay? All right? So that would be the setup of triple integral as an iterated integral of double integral with respect to, in this case, x and z, and then y runs from here to here. After you get this one as a function of x and z, you do double integral with respect to x and z. Okay? So, once you are given what kind of type your domain D is on the x, y, x, z plane, you can write your triple integral all the way down like this, or this, something like this, right? So we will practice this one using many examples in the second part of the lecture of section 12.7. So this is the end of the first part, roughly first half of the section 12.7, which is about the setup, definition of triple integral of a function of three variables, and an iterated integral for those triple integrals, depending on the type of the domain. So this is about the setup. Actual calculation using examples will be done in the second part of section 12.7 lecture, which will be uploaded by Monday morning. Next Monday morning. Monday morning is April, I believe, 6th, right? So today's lecture, first part of 12.7 is considered as material should be covered by the end of this week, the week of March 30th. So this lecture is uploaded on Thursday, April 2nd, so that you can study through the weekend. All right? And don't forget the Zoom office hours for this class is 1 to 2 p.m. every Monday and Thursday. Okay? All right. And I'll see you next time. Thank you.